thanks for joining the webinar today. My name is Chris Posey. I'm the marketing manager at OGI Process Equipment. Today we'll be talking to you about water bath heater basics. Peter Yudovinko and Mike Engel, our sales manager and engineer here at OGI, will be leading the webinar today. If you have any questions or comments at any time, feel free to post in the chat console over at the right-hand side of the screen. We will be saving our answers to the questions to the end of the webinar. So if you see your question go through and it's not immediately answered, that's why. We're just going to collect them and kind of hit them one by one as we get to the end of the webinar. So with that, I'm going to go ahead and turn it over to Peter Yudovinko, our Terry sales manager.
Thank you for joining this webinar. My name is Peter Yudovinko, and I've been with the company for about 4 years now. And prior to that, I've worked at another oil and gas company, supporting projects going into Europe, Africa, and Middle East. And joining me for this webinar will also be Mike Engel.
Hello, this is Mike Engel, and I'm an applications engineer here at OGI, and I work on quoting and designing our heaters.
Thank you, Mike. So today's session, we're going to focus on the heater, basically an introduction to water bath heater, their applications, and design best practices. And feel free to type in the chat questions. We will field them in the order received at the end of the webinar presentation. So today's topics that we'll cover will include an introduction to who is OGI Process Equipment briefly, and then we will focus the rest of the presentation doing a technical review of applications for this water bath heater product. We'll look at site process conditions and ways to control temperature. And then we'll take a look at design standards as they apply to water bath heaters. And finally, look at the major assemblies, their functionality within the water bath heater, and design considerations for those major assemblies. So who is OGI? We're first of all, we're located in Sand Springs, Oklahoma, which is right outside of Tulsa, and we're the manufacturers of the Terry water bath heater product line. This product has been on the market since the early 90s, and we also have another heater product for the commercial and food and beverage applications. So we feel that as a company, our core competency, our main focus is on the heater market. Whether it's in food and beverage or natural gas and the oil industry. And everything that we market, we not only design in-house, but we also manufacture it in-house, and we do a full functionality testing before we ship out the equipment. We'll gas fire all of our fired equipment and tune the burners. And by doing all of this in-house, we have not only been able to maintain the quality that we expect from a product line, but also control our production schedule. And over the last 6 years, we've only had a few late orders, with the longest being 1 week. Additionally, we have implemented many continuous improvements, starting with a new ERP software system in 2015, which basically manages our company from finances also down to the tracking inventory and understanding our vendor performance and leveraging that, and also ensuring that the designs that we create in the office translate over to the shop, and that all of our customer specifications are captured and delivered as expected. And also in the shop, we have implemented automation with automated welders, and these have allowed us to reduce production on the large horizontal seam welds on the shelves or the end plates of the heaters, in some cases from days to hours, and also allowed us to improve or maintain a consistent weld quality, since there's not a variation between welding operators. Of course, we do have code welders on staff that are responsible for welding the high pressure process coil. And finally, everything that we sell, we can support and do support through our service department. Anything from startup commissioning to preventative maintenance, tuning your burners on an annual basis. We could also do repairs, replacements of various components on a heater, and even doing retrofits and upgrades to existing gas trains, or maybe you're wanting to put on a burner management system from a push button relighter system. And also, as a company, we also partner with independently owned manufacturing representatives, and we treat them as an extension of our company to provide local support to our customers. And then last but not least, we are a certified women-owned business, and I know that there's a lot of customers that have diversity initiatives, so just wanted to put that out there. So that concludes the who is OGI and what we manufacture. I will now spend the majority of the rest of the time looking at the technical and the applications of these heaters. And when you think about where these heaters are found, typically in the natural gas distribution, so think of meter and regulator stations, town border stations, city gate stations, essentially where you're reducing pipeline pressure down to distribution level. You also have fuel gas heaters at compressor stations, and this is a variation of a water bath heater with additional controls and communications through a PLC with the gas turbine, for instance. You could have regenerative gas heaters, and this is where you would strip moisture from natural gas coming out of a storage facility. This would be a reboiler like a glycol dehy. And then you may have process heaters for industrial customers that need warmer gas. And again, this is not an exhaustive list, but this is commonly where you find these heaters. Additional applications include propane vaporizers or LNG vaporizers. But for today's session, we'll just focus on a typical water bath heater found at an M&R station. And the most common type of heater will be a natural draft pneumatically controlled heater. This is a standalone in the field heater that doesn't require any power. It will be using the heated gas from the coil outlet to support the burner operation. And for relighting capabilities, you could have a solar powered relighter or burner management system with battery backup. The opposite end of that spectrum would be a forced draft heater with electronic controls and an Allen Bradley PLC. This type of heater is usually at combined cycle plants or power generating stations. These sites may also have emission requirements that will demand a power burner to meet the low NOx or ultra low NOx emissions. And of course, you could have everything in between. In some cases, you could combine pneumatic and electronic controls for certain parts of the heater, or maybe for redundancy purposes. And then I want to talk about a vertical bath heater. This is something that's been around, but it's been gaining popularity, and specifically where you may have a small station where you're fitting in a heater. So space constraint, as you can see, it's going to take about 1/3 of the footprint as opposed to a horizontal water bath heater. And a couple additional benefits to this type of a heater would be higher efficiencies, close to 85% in some cases based on design. And if you were to compare that to a horizontal water bath heater, the efficiencies there could be anywhere between 60 to low 70s. And we'll talk about what kind of design principles you can use to be able to get those good thermal combustion efficiencies. And then finally, the last point would be it's a very quiet operation. Decibel levels 3 feet from this heater could be as low as 65. A conventional water bath heater, horizontal water bath heater, would be 85 or higher, depending on your gas pressure to your burner. And so this is much quieter and So ideal for smaller stations with space constraints or stations where neighborhoods have noise limitations. So now let's talk about what is the purpose of a heater. And so obviously it's to heat gas, but why are we heating gas? And essentially it's to overcome the JT effect, which states that for every 100 psi pressure drop, your temperature will decrease anywhere between 5 to 8 degrees. So with this diagram that I borrowed from Kimra, you've got 900 psi gas going over a control valve down to 200, and you can see it's going to start to fall below freezing temperatures and could freeze up. The reason for this is if you look at your gas composition, you're going to find that it's not just natural gas. You're going to have propanes, butanes, and also elements of moisture. And if this isn't heated, you will run into freezing issues. So to overcome that, you simply heat the natural gas and to ensure that it remains above freezing temperature when it goes across the control valve. And to be able to size a heater to keep it above freezing temperatures, you're going to need to know your process conditions. So to size your heater, I have these items here in red that are required at a bare minimum. If you have this information, any manufacturer should be able to quote you a water bath heater and put together a size for you. And so the first thing is you want to know how much gas you're flowing. And we're also going to want to know your pressure minimum and maximum and your temperature on the inlet. So these are the inlet conditions to the heater. And then your pressure minimum and your temperature minimum after reduction. So these are your owner's desired conditions after the regulation cut. And then I also have glycol type and concentration listed. Not everybody asks for that, and we'll go over that in a few minutes about why that's important. And then if you have a water bath heater specification, also good to know, this is something that will tell us what kind of components you want to use, maybe with a kind of a gas or fuel train you prefer to use, and maybe even hold points and testing or additional fabrication considerations we need to know would be good for us to know so we can properly size and give you what you're looking for. And so here's a diagram of a heater, and we'll lay out a theoretical, process conditions where your inlet points will be listed out here, and then these are your desired output. So in this case, we're looking at cutting gas down to 220 and 45 degree. The manufacturer will then solve how much energy they need to put, how big this heater needs to be able to give you that 45 degree. And in this case, we're looking at making sure that the temperature at the outlet of the heater is 81 degrees. So we know we have our process conditions, we can size our heater. One other consideration we'll have to take a look at is controlling the temperature of the gas or maintaining that 45 degree at the outlet. And there's a couple of common ways to do that. One would be downstream of the regulator. So we're looking, making sure that it's 45 degrees down here if we're keeping up with our theoretical process conditions. And then you have your heater outlet prior to the regulation cut. So here we want to make sure it's 81 degrees. So now let's compare and contrast the two methods. First, we'll take a look at the downstream of the regulator. And here's the picture of that installation on the pipeline. And essentially with this method, you're only adding the required amount of heat. And what I mean by that is, if you recall from the process conditions, we had the pressure minimum and maximum, and there will be fluctuations. So as your pressure increases, you're going to have to overcome a wider gauge spread. So you'll have to put in more energy, more heat. And as your pressure decreases, you won't need as much heat. By sensing it downstream, you're going to take that into account. So this makes it a lot more efficient in controlling your temperature. But there are considerations to this, and I call them considerations because we're going to talk about ways to prevent them from becoming issues. So the first thing is this is a field installed component, so it ships loose. Potential issues include people misplacing them, installing them incorrectly, not knowing what it's used for. Secondly, you're having to run tubing from the heater to this temperature controller. And with that, you may have some debris that gets into the line. You're going to have to make sure you blow those lines out. Otherwise, that debris is going to make its way into the temperature controller and clog it up and prevent it from cycling. And it could be incorrectly installed. You could have these tubes backwards in some cases. We've seen that. And finally, if you have any cathodic protection in your pipeline, you have now connected your heater through the stainless steel tubing to this controller into the pipeline. So let's take a look at proper installation. And this temperature controller on this diagram should be installed horizontally with the dial face here. This is what you would use to dial in your set point to make sure you have that 45-degree cycle. And if you don't install it horizontally, it will be facing up. There's seals in this temperature controller that will start to break down, and then this will prematurely fail, and you'll have to replace it. Also, the thermal well requires about 12 inches in the pipeline before your next elbow, if you need another elbow. So just kind of keep that in mind. We're not sensing flow, so you just need enough space to install the thermal well. And here's an example of an incorrect installation. This is how it's facing upwards. And so again, you could have ice accumulate here and then start breaking down the seal in here. So this is where we custom designed this protective covering. It's an Aquafina bottle. And then we have some tubing that was crossed over, so they had it tubed backwards, and it wouldn't allow this thing to cycle and maintain their bath. And then to isolate from cathodic protection, Swagelok makes isolation union. And on our equipment, we use 3/8-inch tubing pretty much on everything. So that will be the part number if you are interested in what that is. If your heater manufacturer uses a different type tubing, I guess you can go on Swagelok's website and kind of find the appropriate size. But I'll warn you, these are not very cheap, and Swagelok is very proud of their material. So now let's take a look at the second method, which is at the heater outlet. And here's the installation. It's already installed on the heater. This is actually on the truck, ready to be shipped to the customer site. This type of method, it'll maintain your temperature, and we talked about 81 degrees, so it'll ensure that it's always seeing 81 degrees right here. It's not going to take into account your pressure fluctuations, and for that reason, during low flow months, you're going to have a warmer bath. The benefit of a warmer bath is that this promotes a drier combustion chamber. It will prevent condensation from forming. So for the previous method, we would tell you that you should turn your heater off during the summer months or low flow months. In this case, you don't have to do that. And obviously, with it being installed, there's no issues with the tubing being installed incorrectly or any debris, and no installation in the field. So more of a plug-and-play application. However, the disadvantage obviously is less efficient control. We talked about how you're going to have a warmer bath. Well, you may not need that bath to be as warm, so you're putting in more energy, more heat than is necessary. So there's give and takes with both methods. It's up to the owner, I guess, to decide what they prefer, or maybe the technicians really in the field who have a preference. Here's another image of that installation at the outlet. So now let's take a look at design standards that govern the construction of the heater. And the first thing I want to talk about is API 12K. This is a construction specification for the heater. And what it says is that you should be able to remove your process coils in the field. You remove your fire tube from the heater in the field, and you have a removable stack. You have flame arrestors. You have to have a expansion tank and your fuel gas train. Now, API 12K doesn't say how you build it, other than maybe the fact that you should use B31.3, but we'll talk about the standards for a fuel gas train in a minute. We also follow ASME Section 8 Div 1, specifically for this process coil. This is a high pressure process coil. This is what makes your heater a pressure vessel and should be nationally board stamped with a U stamp. And also, although not a code or a standard, GPSA acts as a parent association for gas processing and gas-related industries, and they publish an engineering data book on design and operating standards for these industries. So this is where we borrow or we look to for design best practices, and we'll go into detail of where they apply in the heater design. And finally, your gas trains, they should be built to some type of a standard. ASME CSD-1 is kind of a basis. This is what boiler manufacturers should are complying with for their boilers on their gas train. You can also have NFPA 85, very similar to CSD-1, 86, and then 87 kind of on the high end in terms of additional safeties and redundancy. And if you're using these standards, if a manufacturer is using these standards, they'll be able to give you a safe and reliable heater that works, doesn't have any issues in operations, and has an efficient design. We'll go into detail about things you can do to make sure your heater operates efficiently. And this heater really should last you about 30 plus years. And I'll say that with a caveat, you want to maintain your heater as well, and we'll look at things to do to maintain your heater. So now let's take a look inside the heater and go over the major assemblies. First, we're going to take a look at what we call a bath design. And what we're looking at here on the right-hand side is the cutaway of a heater. We're actually looking from this side here with the burner being on this side and a flame and a stack attached on this side. This is a U-shaped fire tube. Above it is your process coil, where you have cold gas coming in, serpentining back and forth, and heated warm gas coming out on the opposite end of that shell. And surrounding all that will be your bath media. One way we like to look at this heater is this is the engine of the whole operation, your burner. As it warms up, it heats up the fire tube and then heats the bath media around it, which becomes less dense, so it raises up and passes over through the process coils, transferring the heat and the energy, and then as it cools down, it falls back and repeats the process. And in a well-designed system, you'll have this natural occurring convective current. There's not a pump in here that promotes that. This is also a reason why your heaters are round shaped, to help promote this convective current as well. Your bath media will be typically ethylene to water, 50-50. You could also have 40-60 dilution ratio, 40 being ethylene and 60 being water. And then same thing for propylene with 50-50 or 40-60. And we talked about the glycol media having an impact on your design. So let's first compare and contrast the two media, and we'll just do a side-by-side comparison. In our comparison, we're going to take a look at the heat transfer properties of each glycol. And the first thing we're going to look at is the thermal conductivity. And basically, this is the ability of your glycol to absorb and release energy. And with a higher K factor, glycol has just better ability to do that. Your specific heat is how much energy is required to be able to raise your bath by 1 degree. And for ethylene, with this lower number here, it's more efficient at transferring heat. So for these reasons, we feel that propylene is good, but ethylene is much better. And the only thing better than ethylene at heat transfer would be water. However, most people will not use water in water bath heaters, and specific reason for that is, well, you may get freezing issues, which is why glycol is used. But it also glycol also elevates your boiling point, and it has rust inhibitors and corrosion protection built in to protect all that carbon steel inside your shell. And Otherwise, if you used water, you'd have to constantly add water. Your low alarm, your low bath switch would be going off, and you'd have to constantly top it off. So glycol really is the best way to do it, and pretty much everybody does it. But I just wanted to kind of highlight the properties of the types of media and then compare that to water. Now, the environmental aspect, or the impact, I should say, this is where propylene is much better than ethylene, and companies have very strict procedures written around leaks and spills with ethylene glycol. And of course, you could get containment skids. So if you did decide to use ethylene glycol, you could also put a containment skid to prevent that. But I'm not advocating one or the other. I'm just highlighting the differences. And so with ethylene being better at transferring heat, you may think, well, how much of an impact will that be on the heater? And so to do that, what we're going to do is assume a example process condition that will it's kind of a middle of the road heater. We see this a lot at meter and regulating stations, which will result in your process duty being a little over 1 million BTU. And so what we'll do is we'll size it based on propylene and then on ethylene. And in sizing it, we're going to take a look at the size of the shell, and then we'll take a look at how many coil paths and passes, and essentially what your tube bundle is going to look like, your process coil bundle. And so for propylene, we'd need a 48-inch shell by 18 feet long heater to be able to fit the 4 passes coil bundle, which consists of 12 tubes. On ethylene, we'll be able to use a smaller shell because we only have 2 paths and 4 passes with a total of 8 tubes. So there's much less surface area on this 42-inch by 18-foot heater, and because of the better heat transfer property of ethylene, we don't need as much coil surface area. So I talked about how not every owner or utility specifies the type of glycol. So you can imagine in a competitive situation what a manufacturer would lead with. And with a 42-inch heater, you're able to save some money and become more competitive. So let's say you award the person for this heater, but your field crew decides to use propylene glycol because of the more environmentally friendly aspect of it. Well, if we talked about how you need more surface coil area here or less surface coil area for the ethylene because of the heat transfer properties. So you're now using this heater with less surface coil area. So the only other thing you can do to be able to meet that demand and that flow will be to increase your bath temperature. And so notice here we have 152 and 159, relatively close. In order to support that example load that we talked about in this heater, your bath temperature will have to go up to 184 degrees. And the reason why that's a bad thing is the ethylene, the bath limit for ethylene glycol is 180 degrees. So you're 4 degrees above. May not seem like much, but imagine how hot your fire tube, which is the engine of the operation, has got to get in order to warm up your bath to that level. And you're going to get into situations where you're going to start scorching and burning your glycol. Propylene glycol is even more sensitive to heat. The limitation for propylene bath, we would say between 170 and 175 at your maximum. So now you're working with 184 degrees and you're really starting to degrade your propylene glycol. So again, I'm not advocating one versus the other, just wanted to show you the difference and the impact that your glycol could have on your performance of your heater. And all of this will relate to the not only thermal efficiencies, but also the combustion efficiency within the fire tube. So now let's talk about the fire tube design, as we call the engine of the operation. And the length of so the fire tube really defines the length of the heater. And the rule of thumb would be length to diameter 10:1 to 15:1. One of the considerations in designing your fire tube would be something called a flux rate. And this is the heat intensity on the surface of your fire tube. Everything on the surface of this earth has a limit of how much energy it can absorb. Once you go beyond that, you're going to start to burn and scorch it. And glycol is no different. So this is where we look to GPSA and their best practice. And what they say is that if you are using water, then you could go between 10,000 and 13,000. However, for ethylene at 50-50 dilution ratio, you really should be using 8,000 to 10,000. Otherwise, you're getting into a situation where you're starting to scorch and break down the glycol. OGI standard would be between 7,000 and 10,500. And the reason for that range is we may be using a propylene glycol. So really you're between 7,000 and 9,000, 9,500. And then you could use 40-60 glycol to water ratio. So then you can go a little higher on your flux rate. And we assume, we consider this area to be excessive, where you're going to start to really degrade the glycol. If you're operating on below this preferred spread that we have identified, then you're really oversized heater. You've got an oversized heater. And then the example we've used, that would actually, those conditions that we assumed would be around 8,729. And some common flux rate specifications from customers would be just a flat 8,000. And then some say, well, depending on the size of the heater, we could operate on the higher end of that range. One way somebody could get high flux rates would be by using a smaller fire tube or a shorter fire tube, so there's less surface area. And but you still are required to transfer a certain amount of energy, so you're going to have to overfire your burner. And the reason why somebody would actually use high flux rates would be to save money and build a less expensive heater. So let's take a look at what happens when you do have high flux rates. And we've got this smaller under-designed heater, we would call. You save money on your capital expenses, but now you're going to have to spend money on your operational expenses. And those specifically will be with glycol breaking down. You're going to lose your corrosion protection, your rust inhibitors. Your bath can turn acidic, and over time it actually could turn into this dark coffee-looking glycol and turn into sludge that will be sitting at the bottom of your heater. And obviously, with the high heat on the fire tube, you'll start to see hotspots that could eventually lead to cracks and failures, and you'll have a leak into your glycol leak into your fire tube. And also start to evaporate the water with the glycol mix. It's losing its heat transfer properties. So now, instead of the energy going into the bath and then transferring into your process coil, it's all going out of your stack. And so this is where you have the rapid reduction of thermal efficiencies. And so you're overfiring this heater, yet you're still freezing out. The other thing I want to talk about is your on fire tube design is your heat density, and this is essentially the heat released in the fire tube on a cross-sectional area. One way to think about this is the size of your flame relative to the diameter of your fire tube. If you look at this image here on the left-hand side, you'll see this flame, and it's about the length of that fire tube, and that's the reality of how long it will end up being, between 2/3 to 3/4 length of a single pass. And for complete combustion, you're going to want to make sure that there's enough air drawn in around the outside here, all the way to the flame tip, to be able to make sure you burn all those hydrocarbons. So the maximum that we would recommend is 12,500. This actually comes from the Eclipse burner manufacturer. This is a standard burner that you'll find on most conventional water bath heaters. And the issues with having high heat density would be incomplete combustion, like I mentioned, unburned hydrocarbons, and you'll start to see higher emissions and reduced combustion efficiency and higher stack temperatures. Another thing you'll start to see is your stack caps will start to get sooted up, and so poor emissions. Next, let's take a look at the coil design. Like I said, this is what makes your heater a pressure vessel per ASME Section 8-1. And again, you should be getting a U stamp on this heater, which also means that you should be getting a code data book from your manufacturer with all the MTRs, with all the testing, hydro testing, with X-ray, and weld maps. And one thing that we've noticed is that some customers are now asking for heat maps in addition to weld maps. And I would say that as a manufacturer, we'd like to know this up front. So put that into your specifications. It's not really a big deal to provide it, but if you've already fabricated and welded everything together, being able to go back and hunt down where the heat numbers are will be pretty tough. So let us know up front. We have no issue providing that. And one of the testing that I want to discuss will be your X-ray, your radiography. And you have full radiography, and then you have 100% X-ray. And although the two sound the same, they really are not the same. And ASME allows under UW11 to take certain exemptions. And the exemption I want to highlight is the circumferential welds. So you have these tubes with these 180 elbows. There's about two welds on each. And depending on how many elbows you have, you could have anywhere between 20, 30 or more total welds. And with full radiography through the exemptions, you only need to do one X-ray. Under 100% X-ray, there are no exemptions. So that means every single weld is going to have to be X-rayed and provided in that code data book. So we would recommend that you also insist on getting 100% X-ray with your heater. Next, in coil design, we want to take a look at erosion velocity, and the calculation is API RP14E. Here's the calculation. Thing I want to talk about is this C factor. We use 100, assuming you have clean pipeline gas for continuous service. Other manufacturers may use different numbers, and the lower the number, the more conservative it's going to be. Here's a couple of velocity limits that customers have. And then finally, some customers also have SMICE requirements, kind of an additional layer. And here's some typical, and with the state of New York, I'm not calling out state of New York here, but that's one of their requirements. It just makes your coil wall thicknesses much heavier. And as you can imagine, to transfer heat from the bath into the coil will require a larger heater. So kind of something to keep in mind. And then finally, pressure drops. Our standard, or maximum standard, I would say, we won't go beyond 20 psi. Although really our typical on the quotes that Mike sizes were 10, and in many cases actually 5 psi. And common ranges we've seen are 5 to 50 psi. So if a customer tells us they're okay with 50 psi, we're just going to stop at 20 or maybe 10. And your process coil, you could have something called single path, which is basically your coil pipe coming in, serpentining back and forth, and then coming out with your flanges facing outward this way. And then you could also have multiple paths, which would be a header and many pipes coming in, serpentining back and forth. Now, this isn't something that you would specify. This is really something that a manufacturer should do, balancing the required surface area with the size of the shell and making sure it's all fits in comfortably and operates comfortably. And then next, we want to take a look at flame arrestors, which are per API RP12N. And essentially, this is operation, installation, and design recommended practice for the flame arrestors. And in a nutshell, I would say that the flame arrestors should allow air to be drawn into your fire tube for the combustion, but prevent from flame propagating outside. And really, your flame arrestor becomes the barrier between the general wiring inside of your flame arrestor and your hazardous class 1 div 2 area outside of your flame arrestor. And you could have an O type, which is usually for heaters under 2.5 million BTU. You'll have a single cell where air will be drawn in. And then for heaters above 2.5 million BTU, you'll use a box type with multiple flame cell elements that allow more air to be drawn in to support the larger burner in the fire tube. And here's kind of a inside look at what the flame arrestor looks like. And again, this is general wiring. And then with this installed, you are now class 1 div 2. And so the 3-ladder here will have to be per class 1 div 2, unless it's 15 feet from your leak point, which generally are your coil connections. But this is the flame cell here. It's a tightly wound steel, corrugated steel. You really won't be able to see through it, but it'll allow air to come in and then prevent flame from coming back out. And some typical options for flame arrestors include a hinged flame arrestor. This is nice for technicians who need to do burner inspections, operations, or tuning. You're not having to open up and take out this flame cell element, which it actually gets really heavy on larger flame arrestors, and prevent it from damaging. So you just kind of open it up here. You also can get low noise flame arrestors with the insulation that help prevent noise from bouncing out. On our heaters, our typical noise level will be 85, 3 feet from the flame arrestor. With this option here, you'll drop down to 80, and in some cases down to 70. And then finally, you could also get quick opening clamps, which is nice for, again, for technicians who may lose a nut or bolt in the snow. This prevents them from happening. And then finally, the last major assembly will be your stack design. You have people who use stainless steel, and then others who use carbon steel. With carbon steel stacks, they'll have to be painted, and although you're going to use a high temp paint, stacks can operate between 600 and 900 degrees, and in some cases even higher, depending again on your thermal efficiencies and if your burner is tuned. And so over time, that paint will peel and you'll have to paint it. With a stainless steel stack, you don't have to worry about it. We feel that if you spend a little more money on a stainless steel stack, you'll save the headache later with having to paint it. Plus, for aesthetic reasons, it just looks nicer. And for sizing your stacks, the typical rule of thumb is it should be between 2/3 to 3/4 length of a fire tube. The reason for that is specifically for drafting. If your stacks are too tall, then warmer air exiting out of the fire tube will have to travel further and draw in more cold air through the combustion, through the flame arrestor into the combustion chamber. So it'll start drafting harder, and with it, you'll see stack temperatures rising, which also means that you're drawing out heat outside of the fire tube and also the bath. And we feel that that would be unnecessary. You're basically putting heat out of the stack instead of keeping it inside the heater shell. On the opposite side, if you have too short of a stack, then you're going to run into issues with stagnant air because the air is not drafting, it's not lifting up and not drawing enough fresh air in. So you'll have this stagnant air that the burner is going to struggle trying to push out. And then you'll run into issues with burners going out or pilots going out. And also you'll have a hard time trying to tune your burners to keep your proper emissions. So that concludes the presentation. Apologize if I was going very fast. I tried to be cognizant of our time, and it looks like we're 46 minutes in. So now we're going to open the floor to Chris Posey as a moderator to kind of field the questions and answer those as they came in.
Okay, thanks, Peter. At this point, I'm seeing just one question from Brad. Do the different glycols have a different boiling point? Peter, I don't know if you and Mike went on mute, but
I did. I apologize.
I'm not hearing anything right now.
what I was saying was, yeah, they very well may have different boiling points. I don't know exactly what those are, but what I will say is that generally speaking, your bath is going to be at 180 degrees. That's kind of the maximum, and I don't think that's not just an OGI standard. I feel that a lot of other manufacturers kind of follow that. But Brad, if you since we don't supply the glycol, I guess it would, if you looked at a spec sheet on the type of glycol that you were purchasing, you may be able to see kind of what the boiling point is. But I have a feeling that 180 wouldn't be anywhere near that boiling point.
All right, and we have a question from Denise. Could you spend a few minutes talking about the instrumentation on the fuel train?
So, yes, Denise, thank you for the question. On the instrumentation, we do have a separate presentation where we kind of go into details, but you'll have your gas train, which basically, if you're taking your gas at the process outlet, you're going to cut it down to 60 pounds and then support your burner operation. In our case, we'll have the pressure at 5 psi to the burner. On the instrumentation, there's going to be certain safety features implemented. So your high bath temperature, you'll have your low water level switch. You could also put a minimum bath. This is more for fuel gas heater operations. And then, you know, outside of that, you're looking at safety shutdowns to where if one of these alarms goes off, your heater will be shut down and gas will be cut off from going into your burner in your pilot. You could also put in general alarms. So if any of those conditions are met, then it'll send you a signal to your SCADA and alert you that something's wrong with the heater. And then, of course, you could go into different types of relighter systems. And I know you have from the simple push button to more complex relighter and burner management systems, which can control when your burner comes on, when your pilot even comes on and turns off. And so as a manufacturer of water bath heaters, we do use a multiple range of relighter systems, but we also have our own in-house designed relighter system that is Class 1 Div 2. And then we also have a burner management system with extra capabilities. So I don't know, Denise, if that answers your question, but ask away if I need to address that anymore.
Okay, Chester asks, pressure test to establish coil MAOP, testing to 1.3 times MAOP or 1.5 times MAOP.
Okay, so test pressure, coil max. Okay, Mike stepped out. I was going to have him feel that, but I guess I would say 1.5 times to prove the 1.3 MAOP, but let me write that down.
Okay, and if Mike doesn't come back in, we'll be putting the questions and answers in a follow-up email. So if we end up not making it back to this one with a solid answer, we'll speak with our engineers and we will include that. Be sure to include that answer in the email that goes out over the next couple of days. Incidentally, this follow-up email will go out to all registrants, and it will include a link to the on-demand version of this webinar. So if you were having some technical issues at the beginning, or if you just missed something, you'll be able to access this webinar again. So with that, let's go to a final question from Dan. How does higher flux rates affect heater size?
So good question, Dan. Higher flux rates, if you recall, you're using a smaller fire tube, and the fire tube defines the length of the heater. So you're able to have a shorter heater. And if you're using a smaller diameter fire tube and a shorter fire tube, then that's where you'll start to see your higher flux rates or the higher heat intensity on your fire tube, which means that you'll have to overfire your burner or use a larger burner. And if you're using a larger burner now, your heat densities are going to be too high as well because there's no air your flame size is relatively large to the smaller diameter. So now you're going to have kind of two issues with poor combustion and poor thermal efficiencies. But by using a smaller fire tube, that's where you can have a smaller shell and kind of fit the coil and everything else into your heater. So that's how that affects the heater size. Did that help answer that question?
All right. Looks like you did. Great.
So Chester, I did Mike, and he's saying that we do testing 1.5 on pretty much everything. So again, I don't know if that helps answer your question, but that is what we do.
All right. All right. Great. Thanks, Peter and Mike, and thanks to all of you for joining today. We're very happy that you were able to take part in this webinar. We'll continue our series of OGI webinars. We'll have several webinars actually over the next few months. So do keep an eye out. We'll be sending out invitations and making it known on social media. And so with that, I think we'll go ahead and end our session. If any follow-up questions do happen to arise after we're done, you can email us at sales@ogipe.com, and we'll get back with you. So thanks, Peter and Mike. Thanks to all of our participants today, and we look forward to seeing you on future webinars.